Another situation that is relevant to the chat discussion that some of you had going on during class, and it was a very good discussion, much better than anything that was going on in class, I think. Talking about chemical potential energy and batteries storing energy. And there's a situation that's very relevant to that. So let's just start the situation. We're eventually going to get into electron orbitals and so forth, and that's very relevant to the storage of energy in a battery. But for right now, let's just consider a positive charge and a negative charge, like a nucleus and an electron. And this electron is not orbiting the nucleus in any sense, but let's say we're moving this negative charge toward this positive charge. Now, the conservative force and the electrostatic force between positive and negative charges is conservative. That conservative force is in the direction, it's a force of attraction, so the force on the electron moves it toward the proton. Protons have very much greater, well, much greater mass than electrons. It's 1,700 and something, 1,730 times the mass of an electron, or something like that. So if these things are free, the electron does most of the moving. But let's just assume that this positive charge here is nailed down to something. Okay, so it's nailed down. And the electron's approaching it. In that case, the conservative force is in the same direction as the force of as the motion. So the conservative force does positive work on the moving when the charge is moving closer, negative work when the charge is moving away. Now, remember the definition of change of potential energy. Change of potential energy is equal and opposite to the work done by the conservative force, which means that as it moves closer, your PE decreases. You have positive work done here. The change in PE is equal and opposite to that, so it's negative. So you're losing potential energy as you move toward the positive charge. And you're increasing potential energy if you move further away. Now, we haven't done the integrals. It's fairly easy to do. This is an inverse square force. If you integrate an inverse square, you get a negative inverse first power. Which means that in the limit as these things, as the separation of these charges approach zero, you end up with an infinite result. Now that makes it really inconvenient if we want to measure potential energy from zero separation. You already have infinite potential energy, and of course you can't actually have that. So the model doesn't work well, though, if you put your reference point here. You can put your reference points any place else, but not at the position of the positive particle to which the electron or the negative charge, whatever it is being attracted. So what do? You could choose any point other than this as your reference point. But what we're going to do is, and very similar to what we did in the preceding, some of the preceding videos with the magnet and the force, where we let the asymptote be to the x-axis. We're simply going to take infinity as the point from which we measure the potential energy. And in that case, the potential energy starts at infinity, it's zero at infinity, and then as we move in from infinity, not that you can get any closer if you're already infinitely far away, but according to that model, as we move closer to this charge, the potential energy decreases. So it starts at zero and it decreases as we get close, which means that the potential energy versus position function is going to look something like this. Okay, and we're approaching a potential energy of negative infinity as we approach this positive charge. Okay, so there's your potential energy versus position function relative to infinity. So we measure PE relative to infinity. There's our potential energy function of x. Now, having established that, the closer we get, the greater the negative potential energy. If we move from a point closer to a point further away, we see that the potential energy changes in the positive direction. So we have a positive change in potential energy. And that's our potential energy situation with respect to, basically with respect to atoms and molecules, but molecules get kind of complicated. So that's our potential energy function with respect to, let's say, a very simple atom. Let's just now consider a hydrogen atom that consists of a proton, massive proton, much lighter, much less massive electron. Now, this is a schematic, and I don't know why I keep going out of focus here. Let me just put this up for a couple of minutes until we get a little more on the board. It's very possible if the thing is focusing. I don't know where it thinks it's focusing. But okay, here we got we've got the atom, and we consider a hydrogen atom. Now this is not a hydrogen ion; it's a hydrogen atom. It doesn't have two electrons, but we just put two possible orbits for an electron. Now, electrons don't actually orbit like planets orbit, or satellites orbit around planets and planets around stars. And we'll talk more about that much later in the next semester. But we can form a pretty good model, the Bohr model of the hydrogen atom, that has a lot of explanatory power by pretending that these things have circular orbits. Now, which orbit has the greater potential energy? Closer orbit has lower potential energy. Okay? And also, well, let's not talk about kinetic energy yet, but it turns out the kinetic energy in the orbit is equal in magnitude to 1/2 the potential energy and opposite to 1/2 potential energy. It has lower potential energy but greater kinetic energy. And we'll work out the details of why that is. If you want the details, I'll state it fairly quickly. The potential energy gets lower, but it's going in the negative direction, so it's a lower potential energy of greater magnitude. The kinetic energy turns out to be equal and opposite to the potential energy. So the lower potential energy means a potential energy of greater negative magnitude, which results in a greater kinetic energy, because the kinetic energy is opposite to that greater negative magnitude, and also, 1/2 the magnitude. Don't want to go into the details of that. I want to keep this more or less conceptual. Okay. Now, the energy in a battery, and let me do something about focus here, and then we'll come back to that. Let me state that you also can't go from this orbit to this orbit without giving up energy. You have a much lower potential energy. You do have a higher kinetic energy, but it's only your kinetic energy change from this orbit to this orbit is only half as great as your potential energy change. So to get from this orbit to this orbit, you've got to give up energy. You got to, well, what happens is if an electron is in an orbit out here and goes to an orbit in here, it's got to emit a photon, or possibly more than one photon if you got some orbitals in between here. It could go in several stages to get from here to here. In any case, it's got to emit energy. It's got to release energy when it does that. Now, Okay, this is a higher energy. Higher kinetic energy plus potential energy, and a lower energy. So you have a higher energy state, a lower energy state. Now, if you've got two molecules, and let's say a molecule has a nucleus, and it has a cloud of electrons around it, more than one, it's not a hydrogen molecule, at least not in the batteries that we usually use. And you've got another molecule here of a different kind, and it's got its own electron cloud. Now you form a chemical bond when these two can be brought into proximity so that, get rid of our lighthouse, I hope we can keep things in focus now. So you bring these into certain proximity under certain conditions, and their electron clouds can join. The outer electrons will start sharing orbitals with both of the nuclei. So you have something like this. Not very well drawn, but you can kind of get the idea. This is a lower energy state than this. Okay? And the chemical processes that go on in a alkaline battery, let's say, and I'm not going to go into detail about those, mainly because I don't really know the detail. I don't even know off the top of my head of what chemicals are used in there. If I think about it long enough, I might dredge something up out of my ancient memory. But it's these energy changes that are being exploited in the battery. And they're basically, it's a combination of kinetic and potential energy changes. But it's basically governed by the potential energy configuration, by this potential energy configuration, however it applies to the molecules. So, in that sense then, the chemical energy you have in a battery is really a form of potential energy. Not going to go into too much more detail on that. You do want to kind of store away this idea, though, for the force between two charges, okay, the potential energy versus X, and the reference point for the energy having to be, it can't be at zero separation. It's much more convenient to do. It's possible to do it for infinite separation, and that turns out to be the universal reference point for potential energy in atoms and molecules.